Oh, hey.
Hey.
How's it going?
It's good.
Good, yeah?
Yeah, good.
Yeah. Is we going here today?
Yeah. She's in the garage. She's having some trouble getting in the door, but
Oh, I get you.
Oh,
I
I
see.
see.
Hey.
So active today.
Yeah. Alright.
So much energy.
Yeah,
Here,
Auntie
take
Average
your
is-
toy and go.
She's in the kitchen.
Hello, Auntie Average.
So, how are the kids, BB?
they're fine, but they're always running around. There goes one. Little sister is always running around despite her age, and little brother is always running after her, keeping the same pace he always keeps. But if they could just calm down, sometimes it'd be a nice change of pace for once. They just irritate me so much. I hate children.
Alright, so little brother and little sister are at it again, driving the entire family crazy with their antics. Little sister, with her different speeds, different directions, and general craziness, is the prime example of acceleration. Her final velocity and her initial velocity will always be completely different, which is why you would subtract them and then divide them by the time, which could always be facing as she could run all around for quite a long time. But little brother, on the other hand, he's content with a slow but steady pace and always goes at just about the same speed. So he ends up going little further, but at the same speed. So his final distance, is then subtracted from his initial distance and then divided by time to show that he's basically going at an average pace. He's not really increasing or decreasing speed, unlike his little sister, who can run around all day and go faster, slower, or in completely different directions, depending on the situation. Now, dear, calm down. Keep your temper lower. He can get a little physical.
I get you.
Running around, breaking
God.
things. Honey.
Oh, God, you just make me want to punch something.
Alright, that's
Alright,
enough.
I understand.
Alright. It sounds great. Why don't I head into the kitchen with you? Hey, Auntie Average.
Oh, hello.
Anything I can do to help?
Yes, could you cut some potatoes, please?
Oh, I'd love to.
Oh,
There's
fantastic.
always something I enjoy about just peeling a good potato.
Oh, yeah?
Yeah.
That's nice.
Don't know what it is. It's just very satisfying.
That's nice. Hey, Uncle Shorty, could you go get me some tea bags?
Yes, I've got them right here. Actually, I just came back from the supermarket. Here they are.
Okay.
They're just here.
Yeah.
I just dropped them all.
Uncle Shorty, what are you doing?
Oh,
Gosh,
I dropped
Shorty.
too many
What the
things.
heck?
Oh my gosh!
No.
You're
you are
so clumsy, Uncle
My goodness,
Shorty.
what a klutz.
Just having issues today, aren't you?
That's okay. We can make do. It's okay. No, I will do something bad if I have to. Okay. Alright,
My, you're menacing with that knife.
happens. Okay, now let's move on to tea.
So in this scene, Uncle Shorty is dropping tea bags on accident because he's clumsy. And we would use the equation for dropping an object, which would be d equals half at squared. D would be 2 meters because that's the distance that it fell, which I believe is displacement. And A is equal to negative 9.8 millimeters per second squared because of gravity. And time would be the amount of time that it took to fall. And so that is what we're looking for. So we input them into the equation. We get this, we multiply these numbers to find t. And once we square that, we get 3.13 seconds. That is the time that it took to fall for the tea bags.
Here we can model Big Mama peeling a potato using the potato peeler going through a peeled potato. We can use the Big Mama equation involving final initial velocity and 2 times acceleration and direction. And we have the final velocity being how fast the potato peeler is going when she stops peeling, so it's going to be 0. Initial, how fast the potato peeler is moving when it first touches the potato. 2, and then A, which is going to be our U times G, and the G is always going to be 9.8 meters per second squared, and our U is going to be the friction coefficient, which we're going to have equal to negative 0.5 in this case. So once we multiply those, we have A, and there you go. Then we can solve for direction.
Well, honey, let's add the sugar.
You know, I'm thinking you should add the average amount this time.
What?
You know, the average amount of sugar this time.
But I like sugar.
Well, just add your average amount, you know,
Okay.
since you usually do that.
Okay. I like sugar more, but that's
Not
okay.
too much.
Grandma
Don't
doesn't like
worry.
sugar. Here's on the
Got it.
average. Okay. There we go. That seems good. Okay.
Yeah, that
All
sounds
right.
good.
Well, great. Now let's check on the tea.
Oh, yeah, yes. Well, we don't have a kitchen fire this time.
That's good. That's nice.
Yeah.
I haven't had that happen to me in a few days, actually.
It's steeping.
Oh,
In
yeah?
a few days, Auntie, do we need to be concerned?
Well, most likely. That's okay.
Alright, here we have Ani average, and she's making tea, right? So she decides to add some, has a whole pitcher full of tea, decides that it's not strong enough, and decides to add more after she's already made the whole pitcher. So what we can use is this average equation to find her average amount of tea that she added to the pitcher by saying 1/2 times the initial amount that she added plus the final amount.
So how's the wife? She's good. She's good. You know, just bring me that tea. Come on now.
Sorry, but it
People.
should be
I
perfect.
swear. It should be perfect. It should.
Auntie Average is the one who made it. She sent her love.
You know what makes me mad? This tea. You know, just makes me want to just go and punch a freaking lamp. Hold my tea. This horrible tea.
So Big Daddy punches a lamp. So what we would use for that is he does. He's just pissy a lot. So we would use the equation of acceleration. D equals d sub naught plus v sub naught times time plus half a t squared. So both of these would equal 0 because the lamp is at rest just at rest. Time would be time, and so when he punched it, it was only for 0.2 milliseconds. We get A from the acceleration from his fist, which is 25 newtons, divided by the weight of the lamp, which is 5 kilograms, to equal 5 meters per second squared. And to put all of that in, we equal it at 0.1 meters to equal the distance of the lamp that was punched.
That's how you cook with class.
Oh, jeez, we got that.
Don't need no way.
We got fire.
Oh, fire. That's exciting. Glad we're recording, man.
Yeah, it's like.
Oh God. We're gonna blow the kitchen up, alright?
This is what happens.
This is what happens in physics happens.
Yeah, what
Mr. Harvard,
happens?
you better be listening. Come on. Yeah, this is what we normally do because then it creates fires.
Yeah.
Only you can prevent kitchen fires. Smoky can't do it, so you have to. Yep.
Yes,
Alright, back to that. I'm gonna. Exciting. Anyway,